Hello everyone! In this control engineering and control theory tutorial, we explain how to simulate a quarter car suspension model in Simulink and MATLAB when the disturbances are stochastic. Over here you can see a simple sketch of the car. A quarter car suspension model models a suspension of a single wheel. The model sketch is given over here. The model consists of a tire, damper with the damping constant of B, spring with the spring constant of C, and mass representing the quarter of the mass of the complete car. Over here, x is the displacement of the mass or of the vehicle with respect to the equilibrium point, and z represents the displacement of the center of the wheel with respect to some neutral horizontal plane. As the car moves down the road, this point over here will describe this dash trajectory. That is, the center of the wheel will move according to the road profile shown by this green line. In this tutorial, we assume that the z as a function of time is completely stochastic. That is, we will explain how to simulate the response of this system when disturbances, or better to say, the road profile is completely random. By the end of this video tutorial, you will learn how to create this Simulink model modeling the dynamics of the system. Let's run this model and let's see the output. Click over here. And to show the results, we need to click on the scope. Over here, you can see two interesting lines. The first line, that is this yellow line, represents the stochastic road profile over time. This is our disturbance, and the blue line over here represents the position x of the mass. Links to the MATLAB and Simulink codes developed in this video tutorial are given in the description below this video and in the comment section. Okay, let's start with explanations. The first step when modeling any system in Simulink is to understand its dynamics. This equation represents the equation of the motion of our system. In this equation, z is the known road profile, and z acts as an input to this model. In fact, z is a disturbance, and we assume that the disturbance is known function of the time. For example, you can see one generated random stochastic process represented by z. Okay, next, x is the displacement of the mass with respect to its equilibrium position. Then, m is the mass, b is the damping constant, and c is the spring constant. Over here, x double dot is the second derivative of x over time, x dot is the first derivative of x over time, and similarly z dot is the first derivative of z over time. From this equation, we can obtain the second equation. Over here, we simply moved z and z dot to the right-hand side. This is done because z and z dot acts as a disturbance input. Before starting with Simulink modeling, it's always a good idea to properly understand the dynamics of the system. To understand the dynamics of this system, let us derive a transfer function. To derive a transfer function, we need to use the Laplace transform. Over here, the Laplace transform of x, denoted like this, will be denoted by capital X of s. Similarly, the Laplace transform of z will be denoted by capital Z of s. Next, when deriving the transfer function, we assume that the initial conditions for x and z are equal to 0. That is, the initial conditions are neglected. Always keep in mind this fact. Let's apply the Laplace transform to this equation. We have mass s squared multiplied by capital X of s plus b s x of s, capital, plus c, capital X of s, is equal to s b, capital Z of s, plus c, capital Z of s. Okay, let's continue. From this equation, we have that ms squared plus bs plus c multiplying x of s is actually equal to sb plus c multiplying z of s. From this equation, it follows that our transfer function, that is x of s over z of s, is equal to sb plus c over ms squared plus bs plus c. Now, the first question that we need to answer is the following one. What is the DC gain or the steady state gain of the system? Obviously, from here, we can see that the DC gain is equal to 1. For those of you who cannot see this, I will explain how to show that. Namely, from this equation, we have that x of s is equal to sb plus c over ms squared plus bs plus c, multiplying z of s. When computing the DC gain of the system, we assume that z function in the time domain is a simple Heaviside function that's defined like this. 1 for time greater than or equal to 0, and 0 for time smaller than 0. The Laplace transform of this function is 1 over s. When computing the DC gain, we assume that z of s is 1 over s, and the output to this system in the Laplace domain will be sb plus c ms squared plus bs plus c multiplying 1 over s. Okay, to compute the DC gain, we need to go back to the time domain. There is a theorem that's called the finite value theorem that's saying the following. X in the time domain at infinity, that is x at infinity, is the limit value when s goes to 0, s multiplying x of s. Of course, this equation and this theorem is only valid if our system is asymptotically stable. This is actually the case. Okay, now let's use this formula. Obviously, if we plug in x of s from this equation over here, we will have that limit value when s goes to 0. S multiplying x of s is simply sb plus c over ms squared plus bs plus c. And this limit value is obtained by substituting s by 0. This term becomes 0, this term becomes 0, this term becomes 0, and at the end we have c over c. And this is equal to 1. So the DC gain of our system is equal to 1. This means that when we apply a constant disturbance as the input to our system, that is when z is constant, then in infinity, z, or actually x, will follow that input. That is, if the disturbance is a step signal, the output will actually be a step signal also. And this is very important. This means that our output is actually following a disturbance input. Of course, in between we have a transient time, and during transient time we will have oscillations. The fact that the DC gain of this system is equal to 1 will be very useful for verifying the accuracy of the Simulink model. Namely, we will put as an input z equal to 1, and a good verification of our model is to verify that the value of x actually follows 1 after a significantly large time. And this will be verification of the accuracy of our Simulink model. To derive the Simulink model, we first need to rewrite this equation in a more appropriate form. Namely, we would like to have this equation in this form: x double dot is equal to some expression on the right hand side. Let's do that. To do that, let's multiply this equation with 1 over m. Consequently, we obtain x double dot plus b over m x dot plus c over m x is equal to b over m z dot plus c over m z. Next, from this equation we obtain x double dot is equal to minus c over m x minus b over m x dot plus b over m z dot plus c over m z. From this equation, it follows that x dot is equal to an integral of everything that's on the right hand side. That is an integral of minus c over m x minus b over m x dot plus b over m z dot plus c over m z. And everything should be integrated with respect to time. This equation will be very useful for deriving the Simulink block diagram. The next equation is that x is actually an integral of x dot dt. The procedure is the following. First, we will integrate this part to obtain x dot, and then we will integrate x dot to obtain x. And that will be the idea for developing the Simulink block diagram. Okay, let's start with the MATLAB modeling. The first step is to define the model parameters. Over here, I assume that the mass is equal to 300. Then I assume that the damping constant is equal to 300, and I'm assuming that the spring constant is equal to 10,000. The next step is to define the time series of the input disturbance z. To do that, we will need to define an input data structure. This input data structure is necessary for importing arbitrary time series from the MATLAB workspace to the Simulink. Okay, so the first step is to define time. This will be our simulation time. Then, over here, I define a sine signal that's perturbed by a random noise. I'm assuming that the noise is actually white Gaussian noise. We model the white Gaussian noise by using a rand_n function in MATLAB. Then over here, I will increase the variance of this noise, and I will store this noise inside of input data structure.signals1. 1 will correspond to actual number of the input. Since we will have only single input, we will only use 1. And finally, we need to specify the dimensions of our input signal. The dimensions will be 1. And that's it. Next, let's evaluate this script. This is very important before proceeding with the Simulink simulation. By doing this, we will load all the variables and this input data structures inside the MATLAB workspace, and the Simulink can access directly these variables. Okay, to start the Simulink, type Simulink. And over here, click on the blank model. Okay, let's start with the modeling. Over here, for the presentation clarity, I repeated the two derived equations. Our first step will be to model this disturbance input part. We will actually import z as the input data structure defined in the MATLAB workspace. To do that, we need to add the import block. Double click over here and search for import. Expand, and over here type Z. Okay, next click on modeling, then click on model settings, and over here click on data import export, click over here and actually insert or type input data structure and click OK. Now click over here, port number should be 1, then click on signal attributes and the port dimension should be 1. Click on OK. Let's verify that we can properly import Z. To do that, let's plot Z. Double click over here and search for scope. Connect this block here and run the simulation. To run the simulation, click here and click on run. Double click over here and we should see our perturbed sine signal. This means that we have properly imported Z. Okay, let's continue. Close this, erase scope, and erase this arrow. We need to multiply Z by C over M. Multiplication in Simulink is usually modeled as a gain block. Double click here and search for gain. Here it is. Expand the gain block. Double click on the gain block, and here as a gain type C over M. And you can see over here that Simulink can directly access parameters from the MATLAB workspace. This is very good. Okay, connect this part, and now we have C over M multiplying Z. Next we need this part over here, B over M multiplying Z dot. First, let's create Z dot. To create Z dot, we need a derivative block. Here it is. And the output of this block will be Z dot. Next, we need to multiply Z dot by B over M. That is, we need a gain. Here's the gain. Double click on the gain, and the gain should be B over M. Click on OK. Connect this part over here, and let's call this signal dot Z. Good. Next, we need to add B over M Z dot plus C over M Z, so we need a sum. Double click here and search for a sum. Here it is. Now, double click over here to properly align the ports. Erase this vertical bar and place another vertical bar at the end of this string. Okay, and you can see that this port is rotated. Connect this part and connect this part. Okay, now the output of this summation block is actually this piece over here. Next, we need to model these two terms involving x and x dot and to sum them together with this part over here denoted by this red line. To do that, let's first add an add block. Double click over here and search for add. Here it is. We need an additional port. Click here and correct this part over here. I will need plus, this will be this plus over here. Then I have two minus here and here. So let's create these two minus signs. I have minus, minus. Here it is. And magic happens. You can see now that we have 3 ports. This is our plus, modeling this part over here. And over here, as inputs to these two blocks, we will have C over M multiplying X and BM multiplying X dot. Let's start with this term. First of all, we need a gain. Let's create that gain. Double click here, search for gain. Let's rotate this gain. Click on Format, rotate the gain. Connect this gain to this port. Expand this gain, double click on the gain, and the gain should be C over M. And this models this part over here. Notice that the minus sign is actually given here. Okay, the input to this block will actually be x. We will create x later on. Next, let's model this gain, b over m. Double click here, search for a gain, rotate the gain, expand the gain, double click on the gain, and type b over m. Okay, connect the gain over here, and let's continue. Now, we see over here that x dot is an integral of everything over here. The integral of this right hand side is actually something that's very important to understand. Let's analyze this term under the integral. This term is the output of this add block. Now, if you look at this equation, we need to integrate this term over here to obtain x dot. Consequently, let's add an integral term. Double click over here and search for an integral or integrator. Here it is. Connect here, and the output of this integrator is actually x dot. We see over here that x dot should be multiplied by b over m. Consequently, connect the output of the integrator with the input of this gain b over m. And over here, type dot x. Good. Let's continue. Now we have x dot, and by integrating x dot, we obtain x. So double click over here, search for a gain. Actually, not the gain, erase this. Double click over here and search for an integrator. Connect this part over here, and if we integrate dot x, we will obtain x. That is, the input of this integrator is x. We see that this x should go inside of this block, modeling this multiplication over here, c over mx. And over here, type x. Okay, good. Next, let's plot the results. To plot the results on the same graph, we need to use the MUX block. Double click here and search for MUX. Connect this port of the MUX to X, and this port of the MUX connect to Z. This will enable us to plot both X and Z, that is the input disturbance and the output on the same graph. Double click over here and search for scope, and connect the output of MUX to the scope. Good. Now we are ready to run the simulation. To run the simulation, click over here and simply click on Run. Okay, double click over here to see the results. And here it is. Let's see the legend. Click here and click on Legend, and you can see that the yellow line is actually the input disturbance, and the blue line is actually the output x. That is the displacement of our mass. Next, let's learn how to improve the visual appearance of this graph. To do that, do the right click and click on Configuration Properties. Over here, you have several options. We're not going to play with main. Time, you can basically choose several options over here. However, we are not going to play with this option. In display, we can actually set the Y label. The Y label should be Z, X. Click on Apply, and you will see Z and X over here. Good. Next, do the right click, and you can play with the style. Over here, we can change a few things. We can change the line width. For example, the line width should be, for example, 3. Click on Apply, and you can see that now you can clearly see the disturbance. Then you can change the color over here. And let's play with another variable, that is, let's play with x. Click here on x, then select, for example, 4, and click on Apply. And you can see now more clearly the displacement x. Over here, we can see that our output, represented by the blue line, actually follows the low frequency components of our input disturbance. And this is actually something that we expect from the derivation of the transfer function, since the gain of the system is equal to 1. However, let's verify that the gain of the system is actually equal to 1. That is, let's verify that we have properly implemented the model. To do that, we actually need to go back to the MATLAB workspace and we need to model the input disturbance signal to be a step function. Let's do that. Go to the MATLAB workspace and comment this part over here. Now, copy this line to a new line, and over here, erase this part corresponding to the random signal and type once, and here type size input data structure dot time. This will define a step signal. Now evaluate everything, and let's go back to the Simulink and let's simulate everything. Now obviously here there is an error, and we can correct for that error by actually evaluating everything. So I made an error since I didn't evaluate everything. Okay, good. Now we are ready to go back to the Simulink and to simulate the complete system. Let's simulate the system response. Click on Run. Now double click on the scope and let's analyze the results. And we can see what happens. We can see that our system actually follows a step input disturbance, and we can see that after 9 seconds the steady state error is almost 0. This means that we have properly implemented our model. Next, I will explain how to set the initial conditions in this model. Namely, currently we simulated the system response for 0 initial x and for 0 initial velocity of x. Let's set some initial value for x. To do that, double click on the integrator and set the initial condition to be 0.5. This is actually the initial condition for the velocity of x. This is not x. This will be the initial condition for x. That is, by clicking on this integrator, we will set the initial condition for x. Let's set, for example, 1. Click on OK. Let's run the simulation once more. And let's see the results. And we can see that we start from 1, and after some transient period, we return to 1. This means that the DC gain is actually 1. Okay, that's all for today.